Swayam Prabha. Digital India. Educated India.
I want to basically complete that discussion we had on the reaction in a porous catalyst lab, okay, and explain some of the things. So, this is the reaction diffusion equation, and this is what we derived, dCi by dt equals squared minus kCi, okay. And this we derived in the last class, where we are considering the effect of diffusion in the porous pellet, the reaction, and you have the unsteady state term. Now, what I have done is I have assumed that my reaction is first order. The advantage is, when I assume it is first order, it is Ci to the power 1. So, this equation is linear, okay, and the equation is linear, therefore, I can hope to get analytical solutions. I could also assume it is 0th order, in which case this becomes a constant, and I can again hope to get a analytical solution, okay. So, this is assuming first order, equation is linear, equation is linear also for a 0th order reaction, okay, in which case it will be just minus k. So, these terms, this kCi term is called a source or sink term. So, it is a source if it is generating the species, it is a sink if it is consuming the species, that is all. It does not matter, only the sign is different, plus or minus. Now, I want to, in order to solve this, I need to have boundary conditions, okay. So, I am going to assume that Ci at x is equal to L, x is equal to plus L, and Ci at x equals minus L equals C bulk, okay. So, this is the concentration of the reactant in the liquid, and Ci at time t equal to 0 is equal to, let us say, 0. Initially there is no reactant inside, the pellet is there, I mean there is no reactant inside the pellet. Now the liquid is flowing around it with the concentration C bulk, okay. So, that is my initial condition. So, I have two boundary conditions for the second order equation, because my this whole thing is valid from minus L less than x less than L, because that is the thickness of my catalyst pellet, okay, and Ci and this is valid for t greater than or equal to 0. That is the domain over which this equation is valid. I can't use this equation in any other domain, okay. So, now what I want to do is, I want to exploit the symmetry of the problem. This is x is equal to plus L and x equals minus L, okay, and this is x equal to 0, and I have C bulk here, I have C bulk here. So, basically the problem is symmetric in the x direction. If I want to substitute x equal to minus x, I am going to get back the same equation, okay. So, problem or system is symmetric in the x direction. How do I conclude this? I just have to substitute wherever x is there, put minus x. So an x is there only in this term here, the second derivative term. Okay. So put minus x where x is present, and we get the same equation, because the second derivative, when you put minus x here, look at one negative sign, second derivative we get one more negative sign, look at a plus sign. Okay. So that is how you check the symmetry. Otherwise also you can look at the problem and say, look, there is a reaction going on inside, my concentration at the two surfaces are equal, and therefore, this what was happening here is going to be a mirror image of what is happening here. Okay. So when you have a symmetric problem, you do not have to solve for the full domain, you can just solve for the half domain and then find what is happening in the other domain by symmetry. Okay. For more numerically complicated problems, it is much easier to solve for half domain because it is computationally more efficient. Okay. You do not have to solve for the full domain. So basically what I am trying to tell you is, therefore we can solve only from 0 to L. But if I solve from 0 to L, I need to put a boundary condition at 0. Okay. And the boundary condition at 0 will be, because of symmetry, I am going to put the boundary condition at 0 will be dci by dx is equal to 0 at x equal to 0. Okay. Yes, the catalyst is exposed to reactant on both sides and it is coming from both sides, from minus L and plus L. Okay, correct, exactly. The reactant is entering the catalyst pellet which has a thickness of 2L from both sides, and therefore it is symmetric. If this concentration is different from this concentration, it will not be symmetric. Okay, because you have to check not only the differential equation but also the boundary conditions for symmetry. Okay. So now, yes, reactant is entering from both sides. So this is computationally efficient. Yeah, reactant, that is the reason I put Cb here and Cb here, to show that reactant will come from both sides. Okay. And so I am not going to solve this problem with the other thing I am going to do is, I am going to look only for the steady state solutions. Okay. So we look for, at steady state, look for steady state solutions. Which means I just have to put the time derivative to 0. Okay. So the reason why this is called a reaction diffusion equation is because there is a reaction term and there is a diffusion term, and they are basically balancing each other. So now my problem that I am interested in solving is Ci at x equal to L is Cb, and dci by dx at x equal to 0 is 0. This is from the symmetry. Okay. So if it is a reactant, I am expecting the reactant will get consumed as it comes in, right. So the reactant profile will be like this. This is for reactant. Okay. And for product, it will be something else, it will be opposite of that. This is the product. how is the product concentration going to be inside my catalyst? It will be like that. Now it makes physical sense, because the product, the reactant has to diffuse inside. Okay, so this is the gradient, high concentration here, low concentration here, reactant is going to go from high concentration to low concentration. Therefore, it comes into the pellet. Product has to, after the reaction, product is formed, reactant, it has to go out. High concentration here, low concentration here, product goes out of the pellet after the reaction. Okay. So, now what I want to do is just explain to you, this is something which I wanted to do last semester, but unfortunately I could not. See, I have just rewritten that equation. Now what you know is, and this particular equation has been written for here, Ci is the reactant. What I know, the concentration cannot be negative, concentration has to be positive or 0, worst case it has to be 0. Okay. So, this is a positive quantity when I am writing it for a reactant. So, d square C I by, so Ci double dash is greater than 0. So, if you remember your calculus, Ci double dash greater than 0 means what? That means this is the condition for minima, right. For a minima, the first derivative has to be 0 and the second derivative has to be positive. Okay. So, I am just trying to tell you that this is basically a hint to tell you that this concentration profile has a minima inside. Clearly, concentration, what I was trying to explain to you physically, I am trying to explain to you mathematically. Clearly, concentration cannot be having a maxima, because Ci double dash is positive. Concentration of the reactant inside cannot be showing any maxima like I have drawn here. It does not make sense, right, physically. Same thing here, mathematically I am seeing the same thing. So, you know, when you derive some equation and you do all your stuff, so you have to check mathematically and physically whether what you got is actually making sense. Okay. So, the point is, therefore, I am saying this implies Ci has a minima in the pellet. Okay. For the reactant, okay, and that is what I have drawn to you here. It has to be Cb at the boundary, it has to be Cb at the boundary. So, somewhere in the middle, everywhere C double dash is positive, so that is a minima. At this point, derivative, first derivative is 0, therefore, the minima is at the center because of symmetry. If you want to write the same thing for a product, okay, and let us say the reaction is A giving P, what will be the equation? dP d square Cp by dx squared plus Kci equal to 0. Okay. The reaction rate is going to be always given in terms of the concentration of the reactant. So, this reaction rate is not going to be in terms of Cp. The reaction rate will be in terms of the reactant, which is Ci, and therefore, this reaction rate term is the same, only thing is the sign has become different, because now the product is being produced, it is getting generated, okay, and this is your diffusion term for the product. Okay. So, now what I am trying to say is, if you want to do the same analysis as before, you will get Cp double dash as negative. And if Cp double dash is negative, now that implies that you have maxima in the process, in the pellet. Okay. This implies Cp has a maxima in the catalyst. Okay. And that is basically what I have drawn here. The other important thing I want to have done is I am assuming at the boundary the concentration is equal to the bulk concentration. What that means is I am neglecting any mass transfer resistance outside the pellet. Okay. When I am putting this Dirichlet boundary condition, Ci at x equal to L equals Cb implies no external mass transfer resistance. So, this will be the case where if the flow is very fast, okay. So, then there is no resistance, like you have used correlations in the past, right, for Nusselt number in terms of Reynolds number and Prandtl number, for Sherwood number in terms of Reynolds number and Schmidt number, okay. So, when the Reynolds number is very high, your Sherwood number will be very high, Nusselt number will be high, the heat transfer coefficient, the mass transfer coefficient will be very high, okay. So, if that is high, I can for all practical purposes assume that the concentration of the surface is equal to the bulk concentration. There is no resistance outside. So, concentration should think of like a potential, and if there is no resistance, voltage is the same. Okay. So, and this is slightly different from the problem we did last time, where we had the sphere losing heat. I put an external heat transfer coefficient H, okay, to take into account the heat loss. Here also there is some mass transfer taking place, okay, constant species is coming in, but it is governed by the internal resistance. So, in the last class when we did the heat transfer problem, we were talking about the conduction in the sphere and the heat transfer. So, we are only talking about balance between the internal heat transfer resistance and the external heat transfer resistance. Here I am neglecting the internal and then we spoke about Biot number K being very high, K being very low. Okay. The comparison was between internal and external heat transfer resistances, heat transfer rates. Here the comparison is between the internal diffusional resistance and the reaction rate. I am just going to keep my life simple, talk only about two things at a time. Okay, that is the advantage. So, I am neglecting external mass transfer and I am talking about only reaction and internal diffusion. This is internal diffusion because it is inside the pellet. Here we compare the internal diffusional resistance or internal mass transfer resistance with the reaction. Okay. Because the external mass transfer resistance does not exist. In that in the previous heat transfer from a sphere we compared internal and external mass transfer resistances. Okay. So, I think what I am trying to do is I am trying to tell you when you are solving a problem, you need to possibly look at the context in which this problem is there, how it is similar to an earlier problem, how it is dissimilar from an earlier problem, okay. Then only your understanding will improve, okay. So, and if you remember, I said high thermal conductivity, we looked at one limit, then we solved the problem, okay. So, same thing we are going to do now, we are going to look at reaction and diffusion, okay. So, now I am all set to go about solving this, and before I solve this problem, I am going to make it dimensionless, okay. L same thing I have written again, but I am going to make it dimensionless now, okay, because I am trying to talk about comparing two things, reaction rate and internal diffusional resistance. So, when you are trying to do a comparison, you need to be make it dimensionless, because no point me telling you rate is high, low, with respect to what, right. So, you make it dimensionless to get a ratio of two things. So, now clearly C star is Ci divided by Cb, this is the only characteristic concentration. So, I use that for making it dimensionless, and X star is going to be X divided by L, okay. I have only one independent variable, one dependent variable, and I have got my characteristic scales. So, no confusion, okay. And now, if I transform it, what do I get? Di times Cb times L squared, and I should make it C star, right. So, I have just put wherever Ci is there, C star times Cb, and that is it, and this gives me d square C star by d x star squared minus k L squared by di times C star equals 0, okay. And what are the boundary conditions? C star and x star equal to 1 is 1, because now x has become 1 at L, okay, and derivative of C star derivative is 0. So, basically this is one thing here which is represented as phi squared, okay, and this phi squared is k L squared by di, and this is the ratio of two time scales. L square by di represents the diffusional time scale, and Ki, remember, is first order reaction defined on a per unit volume basis. So, it has a time of 1 by second, okay. So, this is time scale of diffusion to time scale of reaction. When you had Reynolds number, you had ratio of inertial forces, viscous forces, okay. So, something like this. Now, instead of forces, we are talking about time scales, okay. And so, basically, if reaction is fast, what does it mean? I mean, maybe I should write this as L square by d divided by 1 by k, that makes it more clear, right. L square by d is time scale of diffusion, 1 by k is time scale of reaction. If reaction is fast, I have K is large. Fast reaction means the rate constant is very high, quickly get over. Okay. So, that means the reaction gets over very, very quickly, the time for the reaction is very, very small. Okay. That is what I mean by saying time scale is of the reaction. So, 1 by K is low, the time scale is low. Okay. So, in the what is the other case? The other case is if reaction is so wait let's do it like this, let's do it slowly. So, reaction is fast, K is very high. So, phi squared is what will be phi squared be? K is high, right? Phi squared is high. Now, you may think why the guy suddenly put phi squared here. There are two reasons, you will see very soon mathematically what is the reason. The second reason, physical reason is this is a positive quantity. Okay. So, I can tell you it is a positive quantity by saying it is phi squared. So, it can't be negative, that is one way to argue. Okay. And the other way you will soon see why I put phi squared. So, if K is very high, phi is high, and that means reaction rate is high, diffusion is slow, and the process is diffusion limited. Okay. Reaction is fast, diffusion is slow, okay, and system is diffusion limited. Okay. So, the diffusion is slow and the reaction is fast. What do I expect? If the diffusion is slow and reaction is fast, I am expecting my concentration profile will be like this, almost flat everywhere. So, this is concentration is 0. All the reaction is reaction so fast, it takes place here. The reaction is confined to a thin zone near the boundary. Okay. Reaction is confined to a thin zone near the surface. The opposite case is going to be reaction is slow, diffusion is fast, in which case phi squared is low. Okay. Here it comes into the pellet very, very fast, reaction is so slow. So, for all practical purposes the concentration is going to be almost uniform, because it comes in and it very slowly reacts. By the time it reacts, it has gone into the pellet. Okay. The reaction is so slow. So, here the concentration is equal to Cb. Okay. And entire pellet is participating in the reaction. Okay. The entire pellet is participating in the reaction. Here, so now when it comes to, like I said earlier, I think we are talking about catalyst active sites, they are usually precious metals. There is no point in here, the entire thing is participating, so it makes sense to put the catalyst throughout the pellet. But here, if your diffusional resistance is high and reaction is fast, all the catalyst here is not even participating in the reaction, because the concentration of the reactant is 0. Okay. So, it does not participate in the reaction, and so putting any catalyst in the center is a waste. Okay. So, basically if you look at catalyst design, you can think of you have to understand this ratio of kinetics and internal diffusion to understand how to design your catalyst. Okay. So, in the first case, the catalyst in the center does not participate in the reaction, and hence we should not deposit catalyst there. Okay. Okay. Of course, the other thing you can do is change the thickness, because that is the thing which is in your control as an experimentalist. For a particular system, you can possibly change the diffusion coefficient by changing the porosity of the catalyst. By when you are synthesizing the catalyst, you can make the thickness of the catalyst big or small and control Thiele modulus. Okay. The other things are not in your control. Reaction rate is possibly you have to change K, you have to change your catalyst to change K. Anyway, so now I will give you the second reason why we use phi squared. So, I have d square c star by d x star squared minus phi square c star equals 0. That is my differential equation, and this is the first order equation, second order equation with constant coefficients. This is a constant, this is all constant. Okay. And how can you solve this? Being linear, you look for solutions of the form e power mx. Okay. So, phi star is going to be of the form e power mx star c1 e power mx star plus c2 e power sec c star as this, seek the concentration as e power mx star. I do not know what is m, I am yet to find out what is m. Okay. So, how do I do this? You substitute this back inside here, and what will you get? M squared minus phi squared equals 0. Okay. I mean, this is your characteristic equation or something what you call earlier. So, in your maths course. So, you just substitute this, you will get m squared and must be equal to 0. So, m equals plus or minus phi. So, if because I put phi squared, I am getting plus or minus phi. If I had put phi for my Thiele model, I would get plus or minus square root of phi. So, I do not want to deal with square root and all that. So, that is the reason, to avoid having to deal with square root, I am calling it phi squared. Okay. So, that is the other explanation. So, now it is clear that this is the solution, and this equation has two solutions. Okay. Now, I need to find these constants C1 and C2 from the boundary conditions. No, when the reaction is fast, the reaction is occurring only near the surface of the pellet. Okay. And therefore, even if you put catalyst somewhere in the middle of the pellet, the concentration of the reactant in the center is going to be 0, because it got consumed in the near the surface. Okay. So, the towards the center, it does not participate in the reaction, it is not contributing to the reaction. So, any precious metal you are putting in the catalyst is not participating, it is a waste. So, if when you do your synthesis of the catalyst, you should synthesize it so that the catalyst is only on the surface. If it turns out you have the opposite situation, that the diffusion is fast compared to the reaction is very slow. Then reaction is slow, you want the entire catalyst to participate in the reaction. So, when you synthesize your catalyst, you want to make sure that the metal is present everywhere inside the catalyst. Okay. So, your concentration of the catalyst inside, concentration of the catalyst now is going to be uniform inside the catalyst, because every part is going to contribute. That is what I am saying. So, in the case where the reaction is slow, the entire catalyst, the whole volume of the catalyst is participating. Okay. Whereas, in the other case, so you make sure that you get maximum reaction, and you make sure that you get the constant catalyst everywhere inside during your synthesis process. I have this thing here. So, now put the boundary conditions. C star equals 1 at wait, let me do the easier one first. dC star by dx star equals 0 at x star equal to 0 from the symmetry. Okay. To differentiate this, that 0 equals C1 phi minus C2 phi. I am putting x star equal to 0. Okay. I keep, so you remember that these are all star variables. Okay. So, this is what have I done? I have differentiated this, put x star equal to 0, exponential of 0 is 1, I am getting that. Okay. Remember, e power 0 is equal to 1. So, what do I get? C1 equal to C2. Okay. And now, the other boundary condition, C star equal to 1 at x star equal to 1, that means C1 e power phi plus C1 e power minus phi at x star equal to 1. Now, I just put, I am evaluating this at x star equal to 1. Okay. I know C is equal to 1, C star equal to 1. So, I get C1 is 1 divided by e power phi plus e power minus phi. Okay. So, I have found my concentration profile. And C star is e power phi x plus e power minus phi x divided by e power phi plus e power minus phi. Okay. I have just found the constants, I put this, and for those of you who are comfortable with hyperbolic functions, this can be written as cos hyperbolic phi x, okay, x star, okay, sorry. Divided by cos hyperbolic phi. So, sin hyperbolic phi, sin hyperbolic x is defined as e power x minus e power minus x divided by 2, and cos hyperbolic x is defined as e power x plus e power minus x divided by 2. So, this is basically the hyperbolic functions, how they are defined. Okay. So, what I have done is I have made the shift from exponential functions to the hyperbolic functions. Divide that by 2, divide this by 2, you get cos hyperbolic phi x, this thing. So, this is the definition of sin hyperbolic, this is the definition of cos hyperbolic. Okay. And what you want to know is that the derivative of sin hyperbolic x is equal to cos hyperbolic x, correct, and derivative of cos hyperbolic x is equal to sin hyperbolic x. You can just differentiate with respect to x, you get this, differentiate this, you get that. Okay. So, basically what have we done so far? We have found quantitatively how does the concentration change inside, the dimensionless concentration. So, you can plot this, and I gave you I told you it will have a minima, okay, but the exact curve, if you were to plot this cos hyperbolic phi x star by cos hyperbolic phi for a particular problem, you will get the actual concentration, okay. So, this is, I believe this is going to be from -1 to +1, this will go from 1 to some value in the minimum, okay, to some value here, to 1. So, this will be your concentration profile in my pellet. Now, there is one concept in reaction engineering where people talk about effectiveness factor of a catalyst. How effective is my catalyst? Okay. So, eta is called effectiveness factor of the catalyst. Okay. And what does it mean physically? I will say, I will measure this as a ratio of 2 reaction rates, okay. That is, this is defined as the rate of reaction in the catalyst with internal diffusional resistance, and this is the rate of the reaction in the catalyst without internal diffusional resistance. Okay. So, that is how I am defining it. I am defining the how effective the catalyst is. Basically, it is a measure of what is the diffusional resistance inside my catalyst. Okay. So, supposing there is no internal diffusional resistance, what does it mean? The diffusion coefficient is very fast, diffusion is very, very fast. What do I expect? I expect the concentration everywhere inside to be equal to the surface concentration C bulk, okay. That is the denominator. When the, so this is evaluated, assuming concentration is equal to C bulk everywhere inside. Okay. And the numerator is evaluated with the internal diffusion resistance, which means the actual profile. This profile talks about the actual profile. Okay. So, when you use the actual profile, when you have the internal diffusion resistance, the reaction rate at different points is going to be different because the concentration is going to be different. Okay. So, when you use this profile, reaction rate that you calculate in the pellet is going to vary from one point to another point because the concentration varies from one point to another point. Okay. So, you have to take a small element, calculate what the reaction rate is, and then integrate it over the entire pellet. That is the numerator. The denominator is concentration is uniform everywhere, does not matter. So, the integration is easy. Okay. So, basically the numerator, that is it, we are done. The numerator is evaluated with the C star of phi x obtained. Here the reaction rate varies from point to point in the pellet. Okay. So, now if I want to calculate this effectiveness factor, I told you the reaction rate 0 to I will do it in dimensional, then I will convert it to dimensionless, KCI dx. Why KCI? Because it is first order reaction, okay, and because the rectangular slab is only dx. So, this volume element, every volume element is dx, okay, multiplied by area, which is anyway same everywhere for the numerator and denominator, it does not matter. Okay, I will put an area, man, okay, and this is integral 0 to L KCB dx multiplied by area. So, this is the rate of reaction with the internal diffusion resistance, which is this is the concentration which I got as a function of x. I have to substitute that here. Denominator is assuming uniform, okay, and so look at it this way, Ci k cancels, a cancels, and I want to convert this into dimensionless variables. So, I am going to call this integral C star dx star will go from 0 to 1, this goes from 0 to 1, the x star, okay. So, what have I done? I am just saying x star is x by L. So, I have a 1 by L from here, I have 1 by L from here, that cancels off, and the limit will now be x star will be from 0 to 1, 0 to 1, okay. So, this is nothing but 1, and all I have to do is, because it is first order reaction, all I have to do is integrate 0 to 1 C star dx star. That is my effectiveness factor. That is C star. So, all I have to do is substitute this expression for C star here and integrate it, okay. This is a constant, it comes out. If you were to integrate cos hyperbolic phi x star, what do you think you will get? I wrote that expression, no? You will get sin hyperbolic, okay, and there's because integrating phi will come at the bottom, okay. This will be sin hyperbolic phi and x star divided from 0 to 1 divided by phi times cos hyperbolic phi. Evaluate this between the limits. So, integral of cos hyperbolic is sin hyperbolic divided by phi, okay, and I am evaluating between the limits. Put x star equal to 1, I get sin hyperbolic phi, x star equal to 0, I get 0, okay. So, this becomes tan hyperbolic phi divided by phi. So, what I want you to do is plot this, I mean go to one of the software packages and plot it. So, eta is defined as tan hyperbolic phi divided by phi. If you were to plot eta as a function of phi, you will get some curve like this. For low phi values, okay, low phi values means low k, low reaction rate, effectiveness factor is 1, this is eta equal to 1. because the concentration everywhere is going to be almost uniform to the bulk, okay. And as you keep increasing phi, only the narrow region is contributing, center does not contribute, so effectiveness decreases. So, this is one way by which you can quantify your efficiency of the catalyst, okay. I mean, earlier I told you whole catalyst is participating, only surface is participating, okay. That was a qualitative argument. You want to get a number, you want to get how effective it is it 1, is it 0.5, is it 0.2. So, that is what we have done just now, how effective is the catalyst quantitatively, okay. So, this is one way. Whatever I have done here can be extended to cylindrical coordinates and spherical coordinates. If your catalyst in the form of cylinder, same argument will come, you can get some maybe Bessel function. If you do spherical, turns out spherical coordinates is very similar to Cartesian coordinates because of a transformation we make, but the same funda is there, same everything goes the same way. Idea is low phi catalyst is effective, high phi efficiency decreases, okay. You can plot this function and you can check for yourself, okay. Phi can go from 0 to infinity, not a problem, okay. Thank you.